Hello everyone. Now let us solve some of the problems, that is slope and deflection by the conjugate beam method. The first example is to calculate the maximum slope and deflection for the beam shown in figure. He has given E and I values here. This is the problem. AB is a beam, 20 kN moment is given at A. This is the given beam. This is the conjugate beam. If you draw the bending moment diagram for this A beam, given beam AB, it will be like this. 20 kN moment at A and 0 moment at B. So it will be a triangular shape bending moment diagram. If you divide by the ordinate by EI, it will become M by EI diagram. This M by EI diagram will become the loading diagram for the conjugate beam. This is the conjugate beam. So this will become a loading diagram. Here he has asked to calculate maximum slope and maximum deflection for this beam. So to calculate maximum, you know that the slope at any point for the given beam is equals to shear force at the same point for the conjugate beam. So to get the shear forces, you need to calculate first the reactions, that is VA and VB for this conjugate beam. So by taking one about B, let us calculate first VA. So you know that is sigma MB equals 0. VA into phi, that is plus, because this side clockwise positive. Then this load will cause anti-clockwise moment. This is what is this load? It is nothing but the area of this load diagram. So it is 1 by 2, base is phi, height is 20 by EI, into, you are taking moment about B. From the B, distance of the CG of this is 2/3 of the base, that is 2/3 into phi, and that you have to equate it to 0. If you simplify for this, you will get this answer for VA as 33.33 divided by EI. Now to calculate VB, you know that VA plus VB, that is sigma Fi equals 0. If you write VA plus VB equals to total downward load. These are the two upward, so VA plus VB, this is downward. So downward total load means it is nothing but area of this triangular load. So it is 1 by 2 base into height, that becomes 50 by EI. So total load is 50 by EI minus VA gives you VB, that is 16.67 divided by EI will be the value of VB. Now he has given the values of E and I in the Newton and mm. So now if you convert kilonewton to Newton to kilonewton, divide by 1000, this mm square to meter square, 1000 square. So if you simplify this, you will get 800 kilonewton meter square as the EI value. Now this is the conjugate beam which you already given. These are the reactions which you have calculated. Now we need to calculate the maximum slope for the given beam. So you know that maximum slope for the given beam is nothing but maximum shear force for the conjugate beam. So for the conjugate beam, usually shear force will be maximum either at support A or at support B. If the VA is greater than VB, the maximum reaction will be, that is maximum shear force will be at A. In case if VB is greater than VA, maximum shear force will be at B. But in this case, the VA is greater than VB, therefore maximum shear force for the conjugate beam will be at A. Therefore, VA is greater than VB, maximum shear force will be at A. Therefore, maximum slope at A for the given beam is equals to maximum shear force at A for the conjugate beam. That is nothing but theta A equals to, here reaction is VA, that is shear force, that is equals to 33.33 divided by EI. And if you substitute the value of EI, you are going to get to this 0.0042 as radians as the slope, maximum slope for the given beam. Next, you have to calculate the maximum deflection. So here you know that maximum deflection for the given beam is given by the maximum bending moment for the conjugate beam. So first we need to calculate the maximum bending moment for the conjugate beam. So let us say that let the bending moment be maximum at a distance xx from support B. Let us assume that here the bending moment will be maximum. Then there is a relation between maximum bending moment and shear force. At the point of maximum bending moment, shear force will be 0. So now therefore what happens now, this is the section or this is the point where the bending moment is maximum. Therefore automatically what happens, the shear force at xx will be, this section xx will be 0. Then how to write the shear force here? If you come from the left hand, upward positive, downward negative. Suppose if you come from the right hand, upward negative, downward positive. So therefore now shear force at x is nothing but it is algebraic sum of the vertical forces either to the left of the section or to the right of the section. Now I am considering right side. So it is minus 16.67 divided by EI, this one, plus this much load. What is this load? It is half base into height. That is half base is x, height is 4x by EI, that is equals to 0. This height we can calculate by similar triangles. This is, you know, that 20 by EI, this total base is 5 and this base is x. So from similar triangles, if you get this height, it will come as 4x by EI. So if you equate this shear force equation to 0, you can solve for x now. So here x comes 2.88 meter, means at a distance of 2.88 meter from B, shear force will be 0 or there will be a maximum bending moment. So now to get maximum bending moment here, what you need to do is you have to write down the bending moment at this section, and in that x equals to, you have to put 2.88 meter. So maximum bending moment for the given beam is equals to, you know, that maximum bending moment for the conjugate beam. So maximum deflection for the given beam is y maximum. So maximum bending moment for the beam where of course here it is at xx, so therefore it is xx. Now let us calculate bending moment here from considering the right side. The right side anti-clockwise positive. So from the left side, you know that clockwise positive. So it is 16.67 into x minus the moment due to the triangular load about this point. The moment due to triangular load means this triangular load is half, base is x, height is 4x by EI, into from this point to this point the CZ distance is 1/3 of the base. That is nothing but 1/3 of x. So now if you substitute x equals to 2.88 meter and EI value, which we have simplified as 8000 kilonewton meter square in this equation, so you are going to get y maximum as 4.01 mm. This is the maximum deflection for the given beam. Now let us consider one more problem here. What he says here, find the slope at A and B, that is both the supports, and deflection at C for the beam shown in figure. So this is the beam shown. He has given the value of EI flexural rigidity as 40,000 kilonewton meter square. You have to use now conjugate beam method. So now this is an unsymmetrical loading, so you need to calculate first RA and RB for the given beam. So how to calculate RA and RB? Just take sigma moment about some algebraic sum of the moments about B equals to 0, that is sigma MB equals 0 for this given beam. So now what happens here? This RA into 8, this is clockwise, and this will be cos anti-clockwise, that is 60 into 4 minus, then this 10 into 4 by 2. This equals to 0. So if you simplify, you will get RA equals to 40 kilonewton. Now to get RB, RA plus RB, if you write sigma Fy equals 0, you know that RA plus RB equals to total downward load, that is 60 plus 10 into 4, 40. That means 60 plus 40 is 100. So total load is 100 minus RA value 40, it gives you RA equals to 60 kilonewton. Now once if you get the values of RA and RB, we can draw the bending moment diagram by calculating the values of bending moment at various points like A, C, B. You know that RA is calculated as 40 kilonewton and RB equals to 60 kilonewton. Now let us calculate bending moment at A, that is simply supported at 0. Similarly, bending moment at B is also 0. Now we have to calculate bending moment at C, either considering left side of C or right side of C. So let us consider left side because there are minimum loads in between AC. So directly what it is now, 40 into this 4, this is clockwise positive. So 40 into 4, that is RA into 4, that is 40 into 4 equals to 160 kilonewton meter will be the bending moment at C. Now if you draw the bending moment diagram, and this will be like this. This is a linear because there is no load here, and here it is a UDL. Under this UDL, the bending moment variation is parabolic. So now the ordinate of the M by EI diagram will be bending moment is 160. Therefore, 160 by EI is nothing but M by EI diagram. Now, if you consider the conjugate beam, this beam will become a conjugate beam, but this loading diagram, the loading diagram of the conjugate beam will be the M by EI diagram of the given beam. So, but here EI is different. What happens here? This is 160. If you come from A, first you have to divide by I. That is 160 divided by I. Next, it is 160 by EI. At this junction, I changes to I. At the same junction, 160 divided by 2I, it will become 80 by EI. Here it is 0. If you join this 80 to 0, this will be the parabolic portion. So now once if you get this conjugate beam and draw the loading diagram on that, now we need to calculate what is here, what is asked, slope at A and B. You know that slope at A is nothing but shear force at A. Similarly, slope at B is nothing but shear force at B. Now, for calculating the reaction at A, now let us take moment about B here. This for this conjugate beam, BA into 8. This is this. Now these two loads are different. This is a triangular load. This is a parabolic load. So minus 1 by 2 base is 4, height is 160 by EI into the distance of CG of this triangle from B. So from here to here 1/3 of 4, that is 4 by 3. Here to here you have to add 4 minus this. Now area of this parabolic diagram will be 2/3 of the rectangle covered by that parabola. That is 2/3, base is 4, height is 80 by EI. The CG distance from B will be 5/8 of the base, that is 5/8 of 4 equals to 0. Or even if you want to simplify this, these areas we can calculate separately, like this as A1 and this as A2. So A1 is 1 by 2, 4 into 160 by EI. This is the area between A and C. X1 bar means the distance of CG of this portion AC from B. So this is, you know, that 1 by 3 of 4 plus from here to here it will be 4. That is 1/3 of 4 plus 4, it will be 5.33. Next, area of this parabolic portion will be 2/3 of base into height. So it comes 213.33. X2 bar form will be 5/8 of B. Now instead of this I can write VA into 8. This is A1. This is X1 bar. This is A2. This will be X2 bar. So if you calculate separately, it becomes easy to write. You can avoid the writing the lengthier equation. Now if you simplify from this, you can write this way or this way. Then if you simplify, you are going to get here VA equals to 280 kilonewton divided by EI kilonewton, and VB is equals to total load minus VA. What is total load? The area of these two portions. This is triangular portion is 320 divided by EI. This parabolic portion is 213.33 B area. So 320 plus 213 will be 533.33 divided by EI minus VA. That is what we got here. So you will get here VB equals to 253.33 kilonewton. Next, we need to calculate the slope at A for the given beam, which is nothing but shear force at A for the conjugate beam. What is shear force at A? That is nothing but reaction at A. So therefore, theta A is the slope at A for the given beam. This VA is nothing but shear force at A for the conjugate beam. So is equals to 280 divided by EI. Simplifying, putting EI value, you will get here 0.007 radians. Similarly, to get slope at B for the given beam, you know that slope at A for the B for the given beam is equals to shear force at B for the conjugate beam. So here slope at B is nothing but theta B, and VB is the shear force at B for the conjugate beam. And here if you come from the left hand, I said upward positive, and if you come from the right hand, upward is negative. So it will be minus 253.33 divided by EI. After substituting the value of EI, you are going to get here minus 0.00633 radians. This is how you have to calculate the slopes at various points. Now he has asked to calculate the maximum deflection for the same conjugate beam. That is maximum deflection. He has not asked maximum here. He has asked only deflection at C. Now deflection at C for the given beam, you know that it is equals to the bending moment at C for the conjugate beam. So deflection at C for the given beam, let us call it as a YC. And bending moment at C, so either you have to consider this portion or this portion. Let us consider left portion here. So it is BA into 4. What is BA? 280 divided by EA into 4 minus the moment due to this triangular load about C. The area of this triangle is 1 by 2, 4 into 160 by EI into the distance of CG of this triangle from C. From here it is 2/3, but now we are taking bending moment at C, therefore it will be 1/3 of base. That is 1/3 of base is nothing but 1 by 3 into 4, that is nothing but 4 by 3. If you simplify this, you are going to get here 693.334 divided by EI. And therefore, after substituting the value of EI, you will be getting here YC equals to 17.33 mm. This is nothing but the deflection at C for the given beam.